Hello everyone. In this video, we are going to learn about the definition of random variable, and we are going to learn it from the perspective of probability theory. So this is in continuation with our previous video on measurable functions. So here we can see the definition of random variable. What's a random variable? Usually, what people think is random variable is a variable, but no, it's not a variable. People think that it's a variable which can take up random values, but it's not. It's a function. So, it's a measurable function. So, it's just a measurable function which maps to the from the probability space omega, f, and p, where f is the sigma algebra on omega and p is the probability measure, and it maps from this domain to the real domain and the Borel sigma algebra. So let's see the explanation. So if you remember briefly from our previous video, we had defined measure spaces. So measure space is nothing but sigma 1 f1. So this is a measure space, measurable space, if f1 is a sigma algebra on omega 1. If you want to know what a sigma algebra means, you can watch our previous video. And let's say there is another measurable space, omega 2 and f2. Now a measurable function is a function which maps from omega 1 to omega 2 sample space, such that for every event present in f2 sigma algebra, for every such a2, there exists a pre-image f inverse of a2 such that f inverse of a2 belongs to the sigma algebra f1. To see this pictorially, we can denote omega 1 sample space as this and omega 2 sample space as this. This is the direction of the function f, which is a measurable function, and this is the direction of the mapping of the inverse of this function, where we'll take the pre-image of it. So let's say there is a set A1 where A1 belongs to F1. So f of A1 would point to A2, where A2 belongs to omega 2. Let's say a function is defined in this way. Now, for every set present inside F2, which is a sigma algebra on omega 2, if I take the inverse of that set, let's say I take any arbitrary set A2, and I take inverse of this A2, it will point to some set in the domain omega 1. Let's name this as A2 star. So f inverse of A2 is equal to A2 star, and all such A2 stars for their corresponding sets present in F2 should belong to the sigma algebra on omega 1, which is f1. If this property is satisfied, that means the function f is a measurable function. Now, a random variable is also a measurable function. The only thing is that the measurable space to which it points to is this measurable space. So a real random variable points to a measurable space, this. So the domain, the sample space, is the set of real numbers. That means all real numbers. And this is Borel sigma algebra. So what's a Borel sigma algebra? You can watch our previous video to check that in more detail, but I'll give a brief summary of what a Borel sigma algebra means. So let's say there is this line, which is a real number line extending from minus infinity to infinity, and all the elements present in the set are real numbers. So Borel sigma algebra is nothing but an open interval from A to B like this. So set of all such sets form a Borel sigma algebra. So this, for example, is a Borel set. Open intervals from A to B, the set of all real numbers belonging in this range. So this is a Borel set. Set of all such Borel sets forms a Borel sigma algebra. And also, not just this, a Borel set can be formed by countable unions, complements, and countable intersections, which means that the complement of this set, open interval A to B, which is minus infinity to A, union with B to infinity, this set is also a Borel set, because the complement of this set should also be a Borel set. And similarly, the union of another Borel set, this is also a Borel set. You can take union of similar such Borel sets. The only thing is that it should be a countable union. And similarly, the intersections of all such Borel sets is also a Borel set. So collection of all such Borel sets forms a Borel sigma algebra. You can verify that the Borel sigma algebra satisfies the property of being a sigma algebra. And from our Borel sets and Borel sigma algebra video, you would also know that this also is a Borel set, the closed interval A to B. This also is a Borel set. This is also a Borel set. And this is also a Borel set. You can watch our video on the Borel sets for seeing the proof of all of these. Okay. Now we have defined the range of our random variable. So our random variable is a measurable function f which points from omega 1 sample space to real numbers sample space like this, such that for any set present in the Borel sigma algebra, there exists, so let's say a set B exists in Borel sigma algebra. So for any set where B belongs to Borel sigma algebra of R, for any such set B, if we take the pre-image of this B, it would be present in the sigma algebra for the sample space of omega 1. For a visual representation of this, we can see something like this. So let's say I have a random variable named x, which is a measurable function from omega 1 to, let's say, r, and this is omega 1, and for representing r, I'll rather represent the real set in form of a number line like this. And let's say there is any Borel set from A to B, so the set of all real numbers in this this is one of such one of the Borel sets. So let's say this is B. There is a function which maps from omega 1, the elements in omega 1, to the real number line, which is x here in this case, which is our random variable, which is also a measurable function. So the x inverse of B will have some elements which would satisfy this x inverse of B. They'll form a set in the sample space omega 1, and this set of elements which are present in x inverse of B, this should be present in F1, where F1 is a sigma algebra on omega 1. If x satisfies this condition, then that means x is a valid real random variable. Okay, so this is the definition of a real random variable. You can also write it in this manner. So the set omega, so the set small omega 1 such that f of omega 1 belongs to the Borel set B, and B belongs to the sigma algebra, the Borel sigma algebra B of R. The set of all such omega 1s, which is this one, which is nothing but f inverse of B, this should belong to F1. If this exists, then that means x is a real valued random variable. So this is the definition of a random variable. So random variable is nothing but a function, a measurable function, which maps from a measurable space, any arbitrary measurable space, omega 1 F1, to this measurable space where the sample space is the set of real numbers, and the sigma algebra is Borel sigma algebra. So any such mapping which satisfies the condition of being a measurable function and which maps like this is a random variable. So this is the definition of random variable. In the next video, we are going to see an example of such random variable, and we are also going to learn about the cumulative distribution functions. Thank you for watching the video. I hope you like this video.